Yeah, the C1K problem. So connecting 1,000 Erlang nodes by distribution doesn't work very well right now. So first a little bit about what I'm doing. That's basically my first project doing Erlang. That's a device for flashing automotive devices. Um, it runs Erlang on FreeBSD and has some gateways with C code on it. And in the meantime, I also went into industrial applications where we have more embedded devices, smaller devices, where Erlang runs almost directly on the hardware. And in this area, there's a request to have a programmability by the industrial people building the factories, basically. And what they normally are used to for programming their stuff and make it move is PLCs, programmable logic controllers. There's a variety of languages, from very primitive assembler-like stuff to pretty high-level stuff. And there is recently also a standard for distributed PLC programming, which just about sounds right for fitting in with an application that also runs Erlang, which is also distributed. And the thing you see here is a function block, which is basically written in a Pascal-like language. It has a little state machine inside, or it has a large state machine inside. It depends on what you write, which has all kinds of conditions. And it has inputs and outputs. The inputs are on the left, and outputs are on the right. On the top part, these are events. That's a new thing for the distributed stuff. And the lower part is basically data, like connected data. So like this. But the events are connected to the data from top with the little boxes. And basically the data is only valid when the event triggers. So this maps pretty nicely to Erlang messages. Basically, the event plus associated data is the message which we send. And these function blocks get mapped to Erlang processes. So one function block with one state machine is one Erlang process. That there are many of those function blocks isn't be a problem for us. So last year I talked a little bit more about this. I just show it very shortly. I wrote a compiler using the tools in OTP that compiles the Pascal-like language, which these function blocks are written in. And there's also another part of the language where you can connect them, and you can also have a graphical model also, but the graphical stuff doesn't exist yet. So there's the typical stuff. You have the files, the brown files, the ST files, which is the name of the language, structured text. You probably never heard of it. Anybody program structured text? Yeah, I did. I had to, because I'm my first user. So I compile this and compile this to Beam files. And the Beam files have some supporting files, basically. The Beam files mainly have the code needed for the state machine and functions that return tables of stuff, like lists of tuples that tell the runtime system what to do with it. And it's basically the two colors of the ST files. The darker one is like a function block, and the lighter one is the application. The application is basically one big function block where you connect stuff together. And you can also have sub-applications, etc., but that doesn't add anything really new to it. And there's basically a function block runtime helper and application runtime helper, and there's also a supervisor, and this all gets connected together. The function block basically run in the PLC F block functions, which are supervised, and which call basically the stuff that's compiled from the ST language is basically a callback module. Like, think PLC F block is a gen server module, and the compiled stuff is a callback module you would write. There's also the PLC up stuff that controls what gets started where and stuff like this and how it's connected. So I was talking about distributed PLCs. So if you want to have this distributed and have an Erlang system, the easy way to just get something running is just use Erlang distribution. And for the first prototype, that's also used and runs. I did this approach. Basically, we have the two nodes here, and each node has its supervised part of the application. So basically, the whole thing is one application. So the application connection file is shared between all nodes. It's basically, and there's an additional configuration file which tells it which function block needs to run on which node. So everything is known in advance. I start all the supervisor starts all the function blocks in order, and there is one block at the end, the PLC mon, that monitors. Basically, it's needed to like start everything up, initialize everything, and then send one start message at the end to everybody. That's the yellow ones on the left side. Basically, I didn't duplicate all the messages because it's mirrored. The right side also has the start messages, of course. And also, it monitors every other node. It monitors every other function block on other nodes, not the local ones, the other nodes, to see if they go away. Because basically, how this thing works is since the PLC stuff doesn't have any failure safeness or any way to restart or recover state or something like this, the first approach to do it, if anything crashes, we crash the whole network basically and restart the whole network again. We want to move to get the Erlang's failure safeness features into this part, but for this we need to change the way the PLC is programmed, add features to the language, which it doesn't have at the moment in the standard. They're still learning failure safeness in distributed systems. The names of the function blocks where you can send of the instances basically of the function blocks where you can send messages to are just registered in global. So I can find everything very easily, which gets us into trouble later, but it made this prototype work very well. The whole thing runs on an Erlang VM that's embedded on the Artemis operating system, which is actually not really an operating system, it's more executive. It's basically you boot into the thing. It's the only thing running on the machine. There are no processes. There's basically one process, and you have threads. And the Erlang VM runs on this. It's basically almost on hardware. I have a TCP/IP stack in this thing, and I can access my files on the NAND flash, but that's about it. This combination is a side project of mine. It's called the Grist project. It's still not released yet, but pretty soon, maybe later this year. So let's talk a little bit more about the application where this is to be used, where we have the use case. It's a research project that a customer of mine is doing, and lots of other research organizations in Germany. Smart factory IT, Industry 4.0, whatever it may be, cyber physical systems, blah, blah. Like, take all the buzzwords in the area and bunch them together. It's a research project. But it's a good research project because we can do interesting things. This is how the hardware looks. Inside are the boards. On former conferences, I've brought these boards and demoed the Artemis running Erlang and stuff like this and the distribution. Now they got the box, so it's getting to look more and more like a product. And this is one of the assembly lines. Basically, what they control is assembly lines. The customer makes transport system for assembly lines. So this includes RFID stuff because you need to find out what you have got. It got stuff to move stuff from here to there, usually ribbons, sometimes like rolls, ribbons, rolls, whatever. And there are little pallets on it or larger pallets depending on what you're building. and they are moved along by the ribbons and stopped by little things going out of the ribbon. That's a stopper, and there you can like pile them up and let them out one by one. And then you have RFID antennas so you can tell what you got there. So you can make like the product can tell the machine what needs to be done next, and all this functionality we have integrated into this box. Actually, the upper box, the lower box is basically a wiring box. That's basically where we attach the cables. So in order to get like a better view of this, I've made a small video. It's like from the demo machine. Say you see the ribbons that are the pallets moving around. These lifts go up and down. If they go up, they lift it off, and then it moves over the side channel. They get fixated because if you need to mount something, it has anti-collision. You need to fix it to so it has a fixed position, because on the ribbon it can move around. RFID system, fixing. Yeah, that's about it. I only had a few snippets. Several people did on their phones while we were building the thing. This machine is actually controlled by Erlang. All of it. And this is how it actually looked on the trade fair. It was shown on CeBIT. It was basically the research project was showing, everybody was showing their stuff, and the ribbons go. You see, you have one in front and one back, and there's also like a human interface robot added to it, like and all kinds of other technology that the other partners were building. So this is a small assembly line we just saw, but if you build assembly lines, you need to like think Foxconn size. So you have hundreds of meters of this stuff, and for the small line, we needed like 13 to 15 nodes, depending on how we built it. And if we want to scale like whole factory size, we are talking about hundreds. And if you talk about Foxconn size, it's thousands of nodes. So we need to connect thousands of Erlang nodes. And we use distribution, and actually I want to keep using distribution, because especially in embedded, it's very nice because you don't have additional encodings and decodings. It's just built into the system. It's relatively lightweight, as long as you don't send lots of data, of course. And it's very convenient to build stuff. But it has issues. So global is slow. Everybody knows global is slow. We found out when we start up our systems and waiting for all the other nodes coming up, waiting for all the names to appear in global. 15 nodes or 30 nodes, depending on 30 nodes took 10 minutes, 50 nodes took 15 minutes to start up. Sorry. It wasn't a problem for the trade fair because, was it me? No. It wasn't a problem in the trade fair. Interesting. Something is pinging. Because basically it started up in the morning, and it's not like workers waiting until the machine runs and everything. And actually all the other partners, until their stuff ran, they took even longer than the NAS to boot. Okay. Oh yeah, it was him. So there's an issue with global. So we need to get rid of global somehow, or augment it, or whatever. And there's also a thing that Erlang distribution in the normal mode tends to make a fully connected network. And so the number of connections in the network is n squared by the number of nodes. So I don't know where with the embedded nodes where we will break. I know 50 nodes work. But I'm pretty sure somewhere between 15 and 1,000 nodes it will break. I don't know if it's 70 or 100 or whatever, but so we can't reach our end goal by connecting all the nodes. short aside, I tried to benchmark different techniques for like replacing global. Um, all the numbers I have is basically if I run it on the embedded network, it takes longer than 10 minutes. And if I start the same nodes on my laptop and going over localhost, it starts in less than 10 seconds. So if you want to measure this, it's very sensitive to latency. I don't think it's throughput in this case, it's latency. So I gave up on this because for this I had to set up like a controlled simulated network with where I can really mock the latency. Just a lesson for somebody who wants to measure this stuff. So I was looking at possible solutions for how to fix my distribution problem. There is recent the output of another research project, SD Erlang, Scalable Distributed Erlang. We will have a short look on it. There's gproc, which is mainly not used in distributed mode because it had issues. But there's a new Lockleader branch which looks promising for fixing the stuff. Then there are hidden nodes. More on it later. And yeah, we could fix Erlang distribution. That's maybe a larger project then. So short look at SD Erlang. Here they have set up a nice website which tells you how to get started. It worked for me. I tried it out. The thing is, what you can get there is you don't have the fully distributed network, but you can define groups of nodes and which can overlap. So basically you have a kind of hypergraph of groups. So you can basically pass messages from, if you have a router on a shared node, you can go from one group to the other group. And inside the groups, they are fully connected again. And they have a name registry replacing global, basically probably grown out of global. It's looking very similar, which only is registering names in one of the groups. So you say, for this group, register this name. So you get around having too many nodes for global. So if you have smaller clusters, so you can like manage the connections of the fully connected network. It's especially nice if you want to like distribute workloads. If you have like a tree-like structure, like you have the subgroup, you have then one member of each worker node in the main node. So clustering could work quite neatly with it. In the end, it didn't fit perfectly for our use case, which we will see later. So let's move on. Yeah, there's gproc had issues with GenLeader. There are several versions, fixed versions or not fixed versions with GenLeader. So mainly people are using gproc not in distributed mode, but in local mode for local registry only. Normally, if you build gproc nowadays, if you don't set a special environment variable, it's not even pulling in the distribution stuff. But there's a new branch from Ulf that uses Lockleader, which uses logs, which should fix the GenLeader problems. Hopefully, it's not very new, but it's like from last year, I think. The Lockleader branch. So it's Ulf still calls it its beta, so it's maybe not right for production. It's supposed to be faster than global. I couldn't measure it because of the issues with my laptop, because global was already fast on the laptop, and I didn't have access to the network, and because it's like someplace else at the moment of the embedded nodes. But the problem is it still does a fully connected network. So you need everybody talking to everybody. It's not fixing the 1,000 node problem for this. It could fix the boot up time for the 15 node problem. That could work quite well, but not the 1,000 node problem. Then, for a long time, there is a concept called hidden nodes in Erlang, which are basically hidden from the rest. They are not visible for the normal nodes command, and they are only connected when you talk to them. So either when you say net ADM ping or net kernel connect, or you send a message to the node, if you know the node name. Then it gets connected. From then on, it stays connected. So you get all the Erlang connection pings, and you have all the stuff like monitoring running. Basically, everything works as usual, except it doesn't show up. So global doesn't see it and can't like wire it in, and you get the fully connected network, because global is the main factor, like producing the fully connected network. So you get a hidden node if you start Erlang with some -hidden option, then it's hidden. This node is hidden from the rest, basically. But you can still see them if you don't use the nodes function with 0 arguments, but with 1 argument, because then you can pass the type of nodes you're interested in. So you can say, show me all nodes that are connected now, or show me all hidden nodes that are connected, and several other options. Quite useful for this. Monitoring works as expected. So once you connect it, it works like normal, except that global doesn't work for it. There are a few other interesting functions if you want to use hidden nodes. There is a Erlang send function with an option, and you can pass the option no connect. I did not figure out what to do with this actually. Basically, what it does is, if it avoids the automatically connecting the node, but it doesn't send the message. So if the node is connected, the message goes through, and you get the usual answer. And if it's not connected, you get the answer no connect. Or not connected, I don't know. You get an answer like, this node is not connected. I don't know. I just put it in for completeness sake, because it's basically only useful with hidden nodes. What's also useful is, if you have hidden nodes and no global registry for names, you need to have a way of sending a process. You have a way to either send the process or get hold of a PID from another node. So you probably sometimes at least will want to use the thing that you can send a tuple, where you have a registered name, a locally registered name on another node, and the name of the node in a tuple, and you can use it like where you use the PID for sending. And it sends basically the message to the other node and looks up the name locally on the other node and sends the message over there. That's built in. And basically all of netkernel is also very useful. So if you want to play with hidden nodes, just read the man page of netkernel from front to back, because almost every second function there is useful for hidden nodes. So, except fixing the distribution, which we'll come to later, that was the overview of the techniques. So let's try to find out which one we pick for this application. Because usually if you have distribution problem, and unless the Erlang distribution protocols are fixed by quite magical things, it usually gets application specific what you want to do. So probably if Erlang distribution is to be fixed or augmented, this will be different augmentations needed for different application areas. So let's look at the assembly line. That's basically the skeleton view of the thing. You have one ribbon in front going this direction, the one in the back goes in this direction, so you can go around. And there's one bridge in the middle where you can also move over. Basically, this place is a repair place, so at the last place it gets tested, and if it's okay, it moves back over, and on the back it gets unloaded, and if it's bad, it goes to the repair place, and what needs to be repaired is shown on a screen for the worker there, and stuff like this. So if you look a little bit inside, that's the drawing from the top of the assembly lines. And what you see here, this is an Erlang node. This is one of our embedded nodes. And the small print below it are the processes on it that need to communicate. So what interests us most, who needs to communicate with whom? which events on data is connected where. So I made a graph which looks peculiar. There's the big fan out in the top. Let's have a look at it. So right in the top, there's a small node that's called init, and this fans out to everywhere. And if you look further, there's also one node with lots of fan out on another one. These are delayed inits basically. So these PLC applications have an init event basically that they need to start running, because if somebody has to send the first event somehow, because the state machine is only triggered to do something if it gets an event. It's defined to do nothing if there's no event. So somebody needs to send the first event, and that's this init in this application. So this is basically the blue boxes are the nodes. So this is how these processes are distributed around the nodes. So it looks a little bit messy. It's everybody is talking to everybody, especially the one node at the top is like pretty connected. So if you like move the processes away and only look at the nodes, so the blue boxes are again the nodes, these nodes will be connected. So if we run this with hidden nodes, not with, I mean, we would get fully connected if we run it normally, but if we use hidden nodes, these will get connected. So it looks pretty clean on the outside, but there's this one node in the middle who needs to talk to everybody for probably obvious reasons, because this init event needs to get sent everywhere. So we would have, I mean, if this is 1,000 nodes, then this one node has 1,000 connections, which is also bad, because if this node breaks, it doesn't help us if the rest would work. So let's have a look again. What if we kick out this node, and this node, all the init nodes, the delayed init nodes, and replace it by some other mechanism? Then the graph looks much more interesting. If I have these processes removed, the other stuff looks more like local communication. So if you look at this one and remove the high fan-out stuff, then we have like chains of like these nodes are connected in one chain, these are in one chain, and there are even some isolated ones which only need to get an init obviously, and then just do nothing. Just run locally. So the node connection graph goes from here to here. I left off the isolated ones. So this would be actually quite feasible to use with hidden nodes. SD Erlang wouldn't help us much, because even if you say, yeah, we have one group, we can like use it like for the groups, for it falls apart, but it would fully connect the group itself. So it might be a solution, but if you have like a very long assembly line and like somehow somebody needs to talk to everybody, this actually falls in two parts, because we have basically a mechanical communication. So we have independent parts which only communicate by the pallet going from there to there, and not by getting a signal back. I mean, the signals are usually anti-collision stuff, like, yeah, this part is free to upstream. And then the thing moves. And sometimes you have like parts where you can like pile up stuff, like having a traffic jam, but one that works, one you can dissolve, and then you don't need the communication, and that's why it falls apart in two pieces. So. SD-Erlang could help, but what looks most like it is like just use hidden nodes. Just use hidden nodes and distribute the initial event, which I only need to do once at system startup. That's also convenient, by another means. For example, by manually introducing, that would be the simplest way, manually introducing init proxies. Send have a simple function block that gets the event and sends it out immediately, and place this on the nodes which are connected anyway. So that wouldn't be a problem. That's an easy way to do. So when we remove the high fan out for this application, hidden nodes would be the solution. You can also, for example, combine hidden nodes with some kind of gossip network if you add other applications to it. Or, for example, if we have the PLC application, needs hidden nodes, but if you have like some kind of compute clusters, because the embedded systems are very small, and if you want like to compute like online planning algorithms, which take a lot of compute power, or can take a lot of compute power, then we might want to have clusters of our embedded nodes and save a big server that stands on the side doing all the online planning stuff, so we can reuse the compute, because these embedded nodes do nothing most of the time. They just sit there and wait for an event. They pull their I/O a little bit for debouncing, but that's it. Fortunately, SD Erlang can be combined with hidden nodes very easily, because when you start SD Erlang, basically all nodes are hidden. You have hidden nodes, but you can group some of them together, which are then not hidden to each other. But the rest is basically the same thing as hidden nodes, so you can combine it quite neatly with other applications. So let's move over to fixing Erlang distribution. I didn't do it. I just looked at it how I would do it, because one always gets to hear in talks and papers that, yeah, we couldn't use Erlang distribution because it's broken for our use case, for whatever reasons. For example, it can't scale to the number of nodes because the fully connected network doesn't scale. There's also an issue if you send one large binary, for example, or a very large message from one node to another node, then since all the messages from one node to the other node are sent sequentially, this large message blocks the line. It takes a lot of time to get over, and smaller messages that need to go from one node to another node have to wait behind it, which can get very messy, because Erlang nodes want to send regular ping messages to each other, like normally every 15 seconds. And if you miss too many ping messages, the connection gets lost. So yeah, distribution falls apart. So there's several approaches, like, but mainly everybody who needs to send large binaries or large messages from one node to another has a secondary TCP connection, where it sends the large data and send only the small messages on the distribution channel, like orchestrating the thing. But it would be kind of neat if this would just work. If distribution would do this for us, like move the large binary over a TCP connection or a secondary TCP connection or a connection pool, and maybe send the small messages as UDP packets. Why not? Or as some kind of reliable datagram system or whatever. There are possible concurrency issues. The thing is, from every node to every node, there is one TCP connection, and there is one LinkedIn port driver. And everything has to move through this port driver. So you have lots of, you have a fan in and a fan out like this. And I think we've seen some of the, if I understood it right, in the former talk, they had similar problems. They had to bunch up together small messages to get rather one big message than have everybody talk to everybody. Because there is some kind of locking involved if you want to talk to the one port. Or at least, I don't know. It might have not been the reason. But this could get messy if lots of processes talking to lots of other processes on the other side. But it might be like, I don't think it's like the main problem. The fully connected network and the head of line blocking are much harder. Then there's also, what if I want to have different transports? I have a research project coming up, going on, to get hard real-time processes into the Erlang VM. So you can write a hard real-time process in Erlang, then you need some other way to do the distribution for these processes, because there are hard real-time protocols and hard real-time networks layers that are used for this stuff. But so you need to divide up, like put the normal messages over the normal distribution and the hard real-time over different distribution. There's also the thing that you might want to have security for, like if you're communicating in a hostile network. In theory, there are in the examples folders of SSL, there is one you can use SSL for Erlang distribution, but it's not built in. But what's built in is like a mechanism to, at least if you can deal with the concurrency problems of the one port, you can build your own. It's pluggable. It's actually, I mean, the documentation is a little bit sparse, but it's not non-existent. There's a command line option, protodist, which takes a kind of module name, which tells the Erlang distribution that you want to have your own module handling the Erlang distribution. Basically, the module that's actually called is mod_dist, so it appends a dist behind it, and that's the actual thing that it calls. And the module needs to implement all these functions. It's basically a kind of behavior, but it isn't one. It's not checked by the compiler. You have to do it by yourself. These functions is basically the whole connection setup and breakdown and all the managing, the orchestrating of stuff. And when implementing this module, you have also there's a this tools module that you can use for most of the stuff. So the hard stuff that's always needed for every distribution, you can pick from the other module, and then you can do your own. What you also need is a port driver that actually implements the transport, because if Erlang sends a message from one node to another, if you have like the send BIF, then you're in the VM, and the VM needs to get rid of the message. So the message doesn't flow over your Erlang module. It doesn't go back top to Erlang and then to wherever. So your callback module basically orchestrates how you set up the connection and everything, and then distribution knows this node has this port, and the port driver you need to write if you want to have a different transport. If you just want to change like session setup and teardown, you could reuse the existing port drivers, but that's probably not much point in this, because if you want to have, for example, you want to have some kind of routing for not a fully connected network, then you need to catch the messages in the port and do the routing there. There is also an example in the source code doing Erlang distribution over Unix domain sockets, which can be found in the examples directory of kernel, I think. And there's also a description about how the driver is built under this link. So it's actually there's actually more there than I thought. It's just a little bit obscure. There are some if you want to build another distribution protocol, there are some things that need to be observed by it, which haven't been like true for all the time, but are true for the current version. Basically, all messages are bracketed between the node up and the node down. So for a current Erlang system, there is no message from the other node coming before the node up, and there will be no message from the other node after the node down. I mean, if it reappears again, then it needs to get the node up again and all the messages. And what's generally true for Erlang, the ordering of messages between any process pair needs to be observed. So you need to keep the ordering. You can't like, if for example you want to send your messages by UDP, you should at least add a sequence number. So you actually know if they're out of order and reorder them. And then you can actually find out if something is dropped, and you can do your own retransmission, or you can just send a node down then. And on the next before the next message, send a node up. Actually, the node down, node up is handled internally already, so you don't have to write yourself. Then there's also another issue. epmd is pretty much wired into how the current distribution protocol works. You need to have a way to find out where is your node. Which port do you connect to? What machine is it on? This is done by epmd, which usually runs once per machine, and is a bit interesting piece of C code, which is not very nice to extend. It's a little bit messy. Since I also needed a epmd for the embedded system, where I don't have processes, because epmd normally runs as an extra process from the Erlang VM. And I don't have processes. It's all together. It's running all together. I only have threads. There is support for running epmd in a thread somehow, but I didn't want to touch it. So what I did is I rewrote epmd in pure Erlang, because there's no reason it needs to be in C, and added a flag to netkernel that if you pass it at command line, you can pass your own epmd module, because epmd needs to be started before the netkernel comes. It needs to be there already. This doesn't take care of having only one epmd daemon per system, which wasn't an issue for me because I only have one Erlang node per system. The system is an Erlang node, so there's one epmd daemon also. But this can be easily fixed. And I have to say, I had to look a lot at the C code of epmd, and if I look at the Erlang code, the Erlang code looks much more manageable to extend to other stuff, which we probably need if we want to fix distribution. I've put a repo link down there. If you go there, you will find an empty repo, because I just put at least the repo up so I can link to it before the conference, because I didn't have time to push the stuff. But I will push it in the weeks after the conference soon. I need to add a few comments of the license and stuff like this. Time for questions.
We have time for a couple of questions before lunch.
Okay. Thomas?
One question is, you had a problem with fault tolerance. You said when one system goes down, all the systems go down.
Yes.
If you have 1,000 nodes, then no matter how fast you start your systems,
yeah, you
if
can.
them all go down, doesn't really make sense. Right?
We will.
That's your main problem, I think.
Yeah. No.
Okay.
we will augment it. Basically, we will put. The problem is if you have a purely event-based systems, and part of it goes down, then you don't know which event you did get and where the state, you don't get the init event again. So you need to have some mechanism to reset up the whole thing. And this mechanism actually needs to be put in this PLC language, because that's actually a lack of the PLC language. It's a problem in this language. I can build this in Erlang, there's no problem, but the PLC language is missing these features. But what we are planning to do is, if you have segments of the assembly line, and what is done in chip manufacturing, there is a kind of protocol which runs on electrical lines. So it's basically, I'm free, send me the next one line. I will send you one now, next line. It's 5 lines. Which have a standard connector, so you can put different modules on chip manufacturing together and connect them. It's a kind of very primitive point-to-point gossip protocol or bus. No, it's not a gossip protocol because it doesn't send on stuff from elsewhere. But it's a very primitive way of controlling the flow in the line. And we will put something in outside of the PLC language. A thing where you can, if this goes away, then every line goes to the default state, which basically prevents this thing of sending stuff into the broken assembly line thing. So you can bring up the stuff separately. I still need to be able to communicate with the thing, but I want to add a little bit Erlang thing, because these function blocks for the PLC, I can also implement them in Erlang. There's a behavior for this, and I basically write two endpoints of these fail-safe connections, and we will like segment the system in this way, and have different applications that are separated by these Erlang parts. So not everything crashes. Of course, it's like, I mean, with the 50 minutes, if you develop on this system, it's hell. Because one crash somewhere, you had one little bug, and then it takes the whole system down, and the next boot takes 50 minutes. That's kind of annoying.
One more question, perhaps?
Yep.
Yeah, I was curious about your teacher there about the EPMD.
It's actually
It's easily solved. You said running EPMD on Erlang nodes instead of a C program is easily solved. So
Actually, yes, because it's just a normal server.
so you start an Erlang node that does nothing but EPMD. Or
Pardon?
you start an Erlang node that does nothing but EPMD. Is that the solution?
Yeah, that would be a solution, yeah.
Okay.
If you wanted to run it on a normal machine.
Yeah.
You start an Erlang node that does nothing but EPMD.
Okay.
For the embedded stuff, I needed something different, because I don't have an extra Erlang node. So I have added an option to the command line, basically, or to the boot line in this case, which starts the internal EPMD at the right point during system startup, before netkernel runs.
the port, so other nodes cannot start it.
Yeah, but there is no other node in the embedded system. There can't be. No, I wouldn't. I mean, if I would run on a Unix system or on a Mac, I would just start one Erlang node, like you said, start one Erlang node with the Erlang EPMD on it. Just doing this, not running distribution. Like a non-distributed node, just running EPMD. And you can start it by the same mechanism where you start how EPMD is started. Basically, EPMD prevents itself that it started twice. It looks, is there another EPMD? Basically, there's I think it's too. It has been a while, and I looked at it. It's too tired. It's basically there's one thing that when an Erlang node gets started, it tries to see EPMD. If it doesn't see it, it tries to start it. And if you have a race of two nodes coming up at the same time, both trying to start an EPMD, EPMD itself prevents of being started twice. And you can use the same mechanism if you use it in an Erlang node. You can even maybe use it. I really would have a dedicated node. I wouldn't on a Unix system. I wouldn't run it on one of the distributed nodes. This doesn't sound right. I think there was one more question. It's okay. Yeah. Thank you.